All right. Okay. Looks good. Hi, everyone. Today I'm going to be talking about, I'm going to be starting a new series, which is working on emulation development. Uh, Kind of the first gateway to emulation development, if you maybe subscribe to the emudev subreddit, is chip8, which is essentially an interpreter which we're going to implement throughout the series. I'm going to be implementing it in C. Initially, I thought maybe I should go ahead and do it in Rust or C++, but I'm just going to do it in C. Uh, I kind of need to brush up on my C skills. I'm kind of rusty in C, so I'm going to try to pick that back up and maybe get more into the language as well, explore some of the features which I didn't learn much about when I was initially learning C. So I'm excited for that. Couple other things. So I have a repo up right now for this. It doesn't really have much in there. Um, Mainly, it's going to be um, some resources which I'm going to be using throughout this series, and I'm going to update this repo with any new resources that I start using, primarily or heavily use at least. Some of these are, so this one is like a technical reference. This is another technical reference which I really like. This one right here. Yep. Another one is the instruction set. There's a little markdown page on each of the instructions. However, you get that information here too. And finally, the STO2 reference, which I'm referencing for because I'm going to be working with STO2, right? That's at least a choice I've made so far. That can change. I can also integrate in OpenGL and as well. However, I'm not. Uh, at least right now, I'm thinking I'm not going to do that. I'm going to stick with STO2 because I mean I want something straightforward. I want to be able to build something pretty quick, uh, and I want to be able to get to being able to visualize or run a test ROM and actually see it working as soon as possible, right? And STO is just a lot easier to work with compared to OpenGL, right? Another thing I did in OpenGL and I think GLFW, right, which I've worked with before, but yeah, if any of you have worked with it, you probably know what I'm talking about. One thing I did want to mention, aside from just implementing the chip8 interpreter, there's kind of many ways you can extend this and take it further. And I think I'll gauge that based on my interest and of course any interest I maybe am seeing being expressed from elsewhere, right, from you guys. So what I'm thinking, at least right now, a couple different things, couple different directions in which we can extend this is I'm thinking I have like a little Raspberry Pi, right? Which is it's a pretty decked out Raspberry Pi. It's a Pi 4, but I mean, what we can do is perhaps deploy our interpreter on here, and I think I've seen this to an extent where people are maybe working on implementing their own drivers to work with an external monitor, maybe like an older monitor. That would be pretty cool. That's one idea, right? But again, I think first we're gonna get to our kind of our MVP, right? Make sure that we're up to spec in terms of whatever the spec is determining or the spec is asking for, and run those test ROMs and see that those test ROMs are working. Once we're there, then we'll think of different ways to extend it. Other ways to extend it could include porting this to mobile. That's one idea. Another idea is um, perhaps like improving the the user interface, the user experience of whoever is working with the simulator, right, or wants to use it. So I mean, yeah, there's a lot of ways to make this more unique, more original, and a lot better than just what the spec demands, right? So that's pretty much what I'm going to be working on. Let me kind of show you what I have set up already. So let me open C Lion. Uh, Here we go. All right. Okay, I hope this is visible. But essentially, what I've been working on so far is just making sure that I'm integrated with SDL2 correctly, right? And I was just doing like a little test demo. So I mean, if actually you can run this, and yeah, there we go. We have our executable, which essentially just produces a white screen at this point, and it's designed in such a way that hey, if you click the little X, it stops, it closes the window and frees all the relevant objects. If or you can also press X, right, uppercase or lowercase to close the window. I mean, extremely simple right now. What we're going to be going forward to is something more complicated, and I think that's something that maybe I'll discuss more as we get there. But maybe something I want to do today is get things kicked off with initializing the structure of chip 8, right? So let me show you first what the spec demands. So again, this site, which is chip 8 technical reference 2, right? Uh, it has it's quite detailed in terms of what the requirements are, not to the implementation, but rather just gives you an idea of hey, this is what this instruction does. This is what these are maybe the registers which chip 8 consisted of. They're 8-bit, 16-bit, etc. So you get a good amount of information so that you can kind of emulate whatever that hardware is in software, right? So like for instance, right, in most cases where a word is italicized is referring to a variable value. For example, if I write vx, the x refers to a 4-bit value. All right. Most important thing to remember is this document is that every TOC link will take you back to the table of contents. Also, links that are not visited will appear in blue while links. Okay, that's fine. That's pretty basic, right? And yeah, this is a little like uh, description about chip 8. And before I jump in, I think it's important to kind of realize, I mean, maybe I can make my motivations clear in terms of why I'm doing this, right? I mean, why emulation development? Why chip 8? Well, I kind of stumbled onto emulation development. I mean, it always kind of seemed cool. I was looking at some of the Game Boy and PlayStation emulators. I used to actually use the PlayStation emulator. I've used it myself, so I was a user of the software, and it's just I guess the knowledge involved with building an emulator kind of gives you a very good understanding of multiple different things, right? Especially like CPUs gives you a great understanding of different CPUs of microprocessors, right? It gives you you know good experience with working with you know windowing software like I mean STL in this case, right? Which I kind of need to brush up on C, so I figured why not. Also, I mean, there's an audio component to this. There's yeah, I mean, there's multiple low-level components involved, which I think is extremely useful if you're trying to come up to speed, in a specific language. This is a very simplistic interpreter. There are more complicated ones which involve a lot of work. Uh, this is, I would say, a decent chunk of work, but not really that much. I think we can get this knocked out pretty quick. At least as I mentioned, the up to spec version of it. After that, we can kind of go any different direction indefinitely, right? But yeah, that's kind of why I am working on this, right? Just to bring myself up to par and see, and I mean, just have something which I can kind of showcase, which is pretty cool, right? So, all right, let's jump into some of the specs, right? So, as you can see, right, this section describes chip 8 memory, registers, display, keyboard, and timers, right? So, this is a nice little memory map, right? Showing you like regions of memory and what those regions correspond to, like what's stored there, right? So 0 through 511, right, is reserved, excuse me, is reserved for the interpreter, right? So that's where the chip 8 interpreter is actually stored, right? And then 512 through 1536, I believe nothing is actually stored there. So yeah, most chip8 programs start at 512, but some begin at 1536. Okay, so chip8 programs will start off from 512, right? Programs beginning at 0x600 are intended, so 1536 are intended for the ETI computer. This is where we're going to store the program and other data as well, right? Which the program creates maybe. All right, so registers, right? So keep in mind we're gonna actually have to obey this memory map and declare and emulate this in software, right? So how does that look, right? So I mean, maybe actually let me pull up this whiteboard, right? So how that kind of looks like is can imagine what we would end up doing is we would have something like our chip8 structure, right? And this is basically like a struct in C, right? And that struct would, comprise of, our memory map, right? Whatever we want to call it, mem map, memory, whatever it is, right? Which is essentially just like you can think of like a one-dimensional array, right? And in this case, our array is 4096 elements, right? Like 4096 bytes, right? So that's something to keep in mind, right? So we have our memory map. What else do we have in here, right? Let me actually pull this to the side. No, thank you, Microsoft. All right, we have general purpose registers, right? So we have 16 general registers, right? And these registers are 8-bit. That's important, right? Then what else do we have? We have sound timer and delay timer. I don't fully understand this so far, but as we read more of the spec, we'll kind of both understand what's going on, right? I don't have a full understanding of what's going on here, right? So I'm kind of discovering that, and you're going to see me discover that and trying to make sense of things, right? Not that I have everything figured out and I've done my homework completely, right? That's why this is kind of a live stream, right? This is hopefully like a back and forth, perhaps questions, perhaps, right? Feedback, discussions regarding like, hey, maybe I misunderstood something, or this is a different way to think about it, right? So I think it helps everyone's learning experience, which is I think great, right? So yeah, we have the sound and delay timers, which I have no idea what that means yet, but that's fine. Then we also have pseudo registers, right? We have the program counter, right? And that should be 16-bit. So that stores the instruction which is currently being executed, right? The address of the instruction which is currently being executed. Then we have the stack pointer, which points to the topmost level of the stack, right? So we have like a call stack, which allows us to like, call functions, right? When we call a function, it's going to store the program counter value in the stack and then update the program counter value to wherever the function is taking us, right? So in order to get back to where you were before after function execution is done, you need to reference the topmost stack element, right, which was the previous location you were in. And another thing which it mentions is that the stack is 16 levels deep. So you can essentially you can have 16 levels of nested function calls, right? So yeah, I mean that's what chip8 actually supports, right? Which is not great, right? You can imagine like your a recursive Fibonacci, right? Uh, Essentially, chip8 can only compute, I would say what, like, um, actually that's not true because recursive Fibonacci would spawn two instances at once, I believe, right? No, actually, I'm wrong about that as well. So it would spawn n minus 1 and n minus 2, which again spawn n minus 1 and n minus 2. It's exponential. So essentially, you would not be able to go more than n equal to 4, right? For sum of Fibonacci, right? So that's not great, right? But that's fine. This is not, the groundbreaking technology. This is, an interpreter from, I believe, the 90s, right, which was spec'd out in the 90s, which were just trying to implement, to get a better understanding of C and also see some of the cool games which were developed against this, right? So yeah, we have the stack pointer is 16 bits, right? Stack is 16. So we have a stack which is 16 elements, right? Which is just an array of 16 elements, right? Where the stack pointer is pointing to the first element, right? And it need not be an array as well. We can implement it as a linked list, whatever. That's fine. But it specifically mentions here that's an array. Again, what an array is, I mean, implementation detail is different. I think we can just stick to implementing it as an array, right? So yeah, 16-bit values again. So 16-bit vals or 16-bit vals. These bit values are important, and we'll come to that, right? Because we need to match the spec. So if we're not, if I declare like 32-bit, right, stack, all the stack elements are 32-bit instead of 16-bit, then technically I'm not obeying what the chip8 spec sets out. So you could argue that, hey, this is not really a chip8 interpreter anymore. The lines are a little blurry there. I don't know who the judge is at the end of the day, but we're going to follow the spec. And maybe after we're done with, the spec'd out version, we can, go off course and, work on something that's maybe even better, right? So, okay, we have then we have keyboard, right? This again comes into our struct, right? Keyboard, which consists of 16 characters, right? 1, 2, 3, as you can see the little character set there, right? So that's fine. Then we also have, excuse me, 16 characters, right? Then we finally have the display, right? Which is going to be 64 by 32 pixel display, monochrome display, so only black and white, right? So that's cool. So we took that black, white, 64 by 32 display, right? And finally, we have, it's not mentioned here, but we'll kind of come to this. We have something called the opcode, right? Which refers to the, the operation code, right? So when we come to looking at instructions, right? All of these instructions are essentially denoted by opcodes, right? 0 and n is an opcode. What does the opcode 0 and n signify? So each opcode has uh, a relevant instruction that it corresponds to, right? So 0NN in this case, I mean, that's a bad example, but 00E0, right? 16-bit opcode corresponds to clear screen, right? Clear the display. 0EE corresponds to return from a subroutine. So each opcode has a corresponding instruction, right? Because instructions, I mean, we understand them in English, but at the end of the day, it's just a number, right? In this case, a 16-bit number. So that's the opcode, right? And that's going to be 16-bit. So let's mention that as well, right? So yeah, I mean, this is kind of very horrible looking diagram, but this is our structure, right? Our chip 8 structure is going to consist of our memory map and then registers, right? Bunch of different types of registers, right? Stack, keyboard, display, etc. So once we do that, right, we need to, so we kind of first need to define structure, and there's different ways to go about kind of implementing this, right? But I think this way is going to be a good idea, just so that we're actually able to test out our code as soon as possible, right? So define the structure, which is not really a big deal. What we're then going to do is try to start displaying stuff. And what that really means is that we're going to connect the display variable, right, which is part of this chip8 struct, with SDO2, right, with SDO2 window and screen surface, right. This is not going to be, this is maybe going to be a little bit challenging just to integrate that, but I guess we'll see what's to come, right. After we do that, then we can actually start uh, working on instructions. We need to define the instructions which are part of chip 8. If we look, right, chip 8 has around, I mean, these many instructions, right? I don't know how many these are. We can ignore these. These are part of Super Chip 48, right, which has somewhat of a different spec, but an upgraded spec. But these are all the instructions that we need to implement in software. You can think of all these as functions that we need to implement, right? Corresponding to chip 8 struct, right? So that's kind of how we're gonna tackle this, right? We're gonna define our struct. We're gonna hook our display object with the STO window, right, and screen surface, and then finally we're gonna start defining instructions, right? Once we're done with that, I mean, we should be up to spec, and we should be able to actually take a test ROM, right? So this is like, these are some games available online which are written out by other people, and we can send that through our chip 8 interpreter and actually see them run, right? Which will be pretty exciting, right? Animation game, whatever it is, right? We can feed that into our chip 8 interpreter. So it's going to be the input is going to be that test ROM, right? Or the program, right, which is going to get fed into our interpreter. Our interpreter is going to interpret, right. It also gives us a good idea in terms of, on a very, very small scale, in terms of how interpreters work behind the scenes, right. I mean, we use a lot of interpreted languages nowadays. I mean, primary example would be something like Python, right, which is an interpreted language. Of course, there's a lot more going on over there, but before you can understand something so complicated, understanding it on a simpler scale is kind of the best way to go about it, right? So then you can actually start maybe coming up with questions on your own and kind of figure out some of the cool stuff that Python is doing, and maybe appreciate some of that more, right? So yeah, that's pretty much it for today, right? I'm gonna, start working a little bit on defining the structure before I start off the next stream, so that guess instead of just me being silent and trying to figure out things, we can talk about them, right? And there'll also be a lot of figuring out, but I just don't want all of it just be that, right? I want to have done some of the homework and then some of the stuff I'm going to figure out on the spot. So yeah, that's pretty much it. Thank you so much. And yeah, let's jump into it. I'm excited. Thank you.